Is it okay?
Okay.
Okay, thanks. Hi, everyone. Very happy to have you today. Today we will talk about preparing the guardrails for Istio at scale. So first, a little bit about myself. Oh, what? Oh, sorry, it doesn't move. Sorry. Okay. No, doesn't work. Sorry, I have a bit issue. Okay, sorry. So about me, my name is Raphael. My Twitter name is Lainra with a 1. I'm a member of the Mercari microservices platform team. And feel free to follow me on Twitter or ask me anything if you want. Today's agenda. So first we will go explaining a bit about Mercari in few numbers. Then we focus on refining the Istio maintenance experience. Then about how to make Istio changes observable. And finally, how to protect Istio and its users from themselves. So first about Mercari in few numbers. We have around 150 microservices with one namespace per microservices. And at peak on our API gateway, we're around like 100K RPS. We have one main production Google Kubernetes cluster that is shared by everyone, around more than 300 developers and more than 3,000 pods. So let's talk first about how to refine the Istio maintenance experience. So we go first into exploring what are the options to install and configure Istio for production use. So we can see a timeline from Istio 1.0 to 1.6. And at Istio 1.0, there were only 2 options to install and configure Istio, hem-based template and kubectl apply, basic raw manifest apply. The next tools came around 1.4, which are istioctl. And in 1.5, we had istioctl upgrade that became stable, and also the Istio operator that was released. And finally, in 1.6, the Helm-based installation was deprecated. So before going further into explaining how we configure Istio, we want to share our approach to adopt Istio. So basically, we enable as few features as possible by having a gradual adoption and gradual migration of our microservices in Istio so that we can support the microservices and support Istio in an acceptable way. So we started Istio around 1.1. So at that time, there were only the hem option available, but we were really afraid of the Istio instability plus the hem magic. A lot of things happen in hem templates you may not know and still not know now. So we decided to apply the manifest ourselves to at least have a sense of control. So how we did that is to first generate the manifests from the hem templates and manually review those manifests and pushing the PR with all those configuration and merging it. Then we apply all those manifests. And finally, we only used the minimal components for the mesh. So the control plane, pilot, and the sidecar injector to inject the sidecars into our pods. And it was very, very painful. Here is a screenshot of one of our PR. We had to upgrade Istio to 1.2. And you can see there is around 3,000 lines of configuration changed and around 100 files to be reviewed. So that's a terrible review cost. And it's really error prone to have that much configuration to be reviewed by humans. And finally, the lead time for those minor version upgrade is very long, and we didn't have much confidence in doing that. Then we had to wait until Istio 1.4. As we saw in the timeline, there were no tools between 1.0 and 1.4 to make it like production ready. And then in 1.4, we have istioctl that graduated. And with that, it introduced a new custom resource in Kubernetes to declare the Istio state called Istio control plane. And also another command with that binary came upgrade as an experimental tool. It was a new tool to streamline the changes in Istio state, but still experimental in 1.4. it graduated in 1.5.2. And at the same time, the Istio operator was released, but the state reconciliation is pretty scary. To have a controller to apply continuously your changes is something that we are pretty scared about. And we were used to apply state by having Terraform. So we wanted to keep the same approach. So we finally decided to use istioctl for changing or upgrading our installation. So how do we go from our manifest-based installation and configuration to Istio control plane format? So there is a way to migrate the hems values.yaml that is used to generate the hems template and hems configuration. And this command is istioctl manifest migrate. So in input, it takes the values.yaml from hem and it outputs an Istio control plane YAML file. And then it's not really straightforward because between versions of Istio, there are some values that are deprecated or modified. So for example, what we had is like third manager is not in the same place than before, we had to remove it, or the gateways are defined differently than previously, and you have to change the way they are declared. So we need to make sure that all components not used are disabled, because it's not very clear, especially when you have new components that are enabled by default. You need to make sure that they are disabled. And finally, in provision for the upward compatibility, when hem is deprecated, we move some values.global parameters inside the KTS parameters within each component to have the upward compatibility. So how to apply the new configuration? This is what it looks like when you run the istioctl experimental upgrade with the Istio control plane YAML. So you can see it checks the versions, planned upgrade, and it gives a lot of diffs. We will show later some of those diffs, but before that, we will explain the process that we use exactly the same process for changes or upgrades. The great thing is that istioctl upgrade gives a diff between the configurations, whereas when you use, for example, istioctl manifest apply, it will not send the diff. You need to do it by yourself prior to use the command. And then what we are doing with the Istio upgrade command is first we run it with dry run flag, so that we can get the output, expected output. Then we send that diff output to a PR along the changes to the configuration. We get reviewed, approved, and we merge it. Then finally, we apply the merge configuration by removing the dry run flag from the command. And finally, we pray so that nothing breaks unexpectedly. You never know what may happen. Here is a simple PR body. So it fits, like it's from 1.5.2 in our dev environment. When we upgraded from 1.5.1 to 1.5.2, there's only that much output, but there is a lot of room for improvement to make it even more clear. But at least we have only that diff compared to our 100 files to review before. So after moving to the new process, our lead time for upgrading versions was shortened by 300%. And we really gained much more confidence into changing and upgrading Istio more often. So about the takeaways on refining the Istio maintenance experience, the first is that hem is now deprecated and istioctl is much easier to use, but still room for improvement. Kubectl apply, so the raw manifest approach is too costly to maintain, so it would be better to use istioctl instead. Then you need to convert the hem configuration to the istioctl CRDs, so Istio control plane for 1.4 and Istio operator for 1.5, to not be confused with the Istio operator that is a controller in the cluster and the Istio operator CRD that is a file version. Then finally, it's really recommended to combine versioning. So for example, using GitHub PR with istioctl to get a safer environment and allow review of new changes. So now we applied our changes, but wait a minute. How can we know if everything is going fine? How can we observe that everything is going fine? So we need to make Istio changes observable. And how to make this? First, we need to understand what happens when Istio changes. And the first step for that is about monitoring Istio. Two ways, the Istio default stack or some specific observability platform. The Istio native stack is pretty rich and the default dashboards are helpful. So it fits most use case for users. But depending on your case, you may have already an observability solution. So we maybe wish to integrate it with existing solution. The thing you need to think is, do you want to expose new dashboards and new UI to your users? So in many cases, when you integrate an existing solution, it is the cheapest decision, especially on the user experience, because you don't have to have your developers to get used to a new UI, a new tool. So that's the direction we took. We integrated Istio monitoring with our existing Datadog with the Istio integration. Here is a glimpse of what looks like our production dashboard for Istio. We have some SLOs, Istio-D, so control plane and data plane related metrics. I will not go too far because we will explain some later. So then second part is, what do we need to observe in Istio? In Istio, there are two parts. The control plane, represented by Istio-D with 1.5, Istio pilot and others before 1.5, and the data plane that is your envoy proxies throughout the mesh. So how do we observe the control plane? First, we want to think about use metrics, so utilization, saturation, errors metrics. And when it's control plane, it's about CPU, memory, and concurrency in the Golang stack, the guardrails extra. And the second one is the red metrics, the rate, errors, and duration, more about the workload metrics, where in the case of the control plane, it's about pushing configuration to the proxies. So the most important thing is to check the count of config pushes, their duration, and their errors. On the data plane, envoy proxies process requests. So most of their metrics will be related to the connections or requests that go through. But for the use, we have the same metrics as the control plane, CPU, memory, concurrency. And for the red metrics, that's where it's different. We have requests instead of config pushes. Of course, you get some config from pilot, but the main metric here is the how many requests go through, how many errors go through the proxy, and what is the latency, the duration for those requests. It's easier to observe the control plane because you have one component versus many proxies in the data plane. And thanks to that, you can regroup all metrics into one dashboard for the control plane. Then on the data plane side, before having to observe everything, you can have an overview of the sidecars in the same dashboard as the control plane to help observe. Some examples of what you can have is number of sidecars in the cluster, the average CPU usage per sidecar, the average memory usage per sidecar, and some heat maps to easily check the outliers. But it only covers our use metrics. So what about red metrics? So we check how to observe the data plane. Since we know that checking all traffic for all proxies is almost impossible for several reasons. Most metrics are application specific. All applications are not exactly homogeneous. The configuration may change also per namespace, and having that much information in one dashboard is pretty hard. So how can we solve it? Then we've thought about this, and then we found a way by defining basic acceptance tests. So acceptance tests, they need to be simple first, easy to observe because the end goal is that you observe what is happening, and covering the main scenarios for your mesh. So in our case, we have several combination of tests. We have always on the left a load generator we call load tester, and we have two cases with Istio sidecar proxy without Istio sidecar proxy. And on the right side, we have a different kind of service, gRPC service, for example, HTTP 1.1 service with and without sidecars. Also, we have some case for headless services because headless services have been known for a long time to be quite conflicting with Istio. And it really helps to have all those cases because you can understand exactly what's happening, which case is failing at some point when you have some changes. So your acceptance tests, ideally, they should be based on existing services, but it's not always the case. It's pretty hard to use sometimes the existing services to do that. So you can replicate instead a miniature of your main services and test against it. Actually, we do a mix of both, and it works quite well. So what we do is generating a live traffic continuously against those services and get success rates. That's what it looks like in our cluster. We have within one namespace called acceptance test. We have a lot of different pods running one specific test. And we get continuous metrics in our data dashboard and the success rate. It's pretty easy to observe when we have a change if it's not 100% anymore. Then about the takeaways for making Istio changes observable. First, we need to choose the observability stack for Istio while always keeping the cost in mind, especially the user experience. Second, the control plane is easier to observe than the data plane. And we need to simplify the data plane observability with acceptance tests to observe that. Finally, having everything in a centralized place to observe changes make them easier. So if you can have the acceptance test and the control plane metrics at some point in the same place, it's easier to observe in a glimpse what is happening in both control plane and data plane. The last part is about protecting Istio and its users from themselves. So I think that's the main topic for this talk. First, why do we need to protect Istio and its users? First, the reason is that we have a shared service mesh. So the service mesh is common to all users. It means that any change to it may spread across the whole mesh. That also means that any misconfiguration will spread it, either unintentional or intentional. On top of that, humans are error prone, and both users and operators are humans. So the result is that errors will always happen, and possibly with a large blast radius. So I will show one case of misconfiguration example. So for example, in production, we have a client that is calling an ingress gateway. And the ingress gateway has a proxy, is part of the mesh. And we have a virtual service defined in our namespace to route the traffic to the production payment service V1. So we have 100% of the traffic going to those two payment V1 pods. Then what happens is I have a configuration change. Someone is changing the subset to go to V2, but I only have V1 pods running. So what happens when I don't have a V2 and I change the virtual service subset? I drop all the traffic. I sync all the traffic to something that doesn't exist. We get 0% of the traffic going to the payment V1. So we just dropped all our production payment traffic. I really don't want to be on page, or I wish to be on vacation the day it happened. But let's calm down because it didn't happen to you yet, hopefully. If it happened to you, feel free to share your experience after the session. Would be really happy to talk about. But we will explain about how to prevent it from happening in the next part. So how can we mitigate errors and their impact? Two things. First, we need to understand as to how the resources are changed. And the second one is about creating the appropriate safeguards. So to understand how changes are done, we will explain a little bit what our workflows in our company to change Kubernetes and Istio configuration. The first one is a developer writes some configuration in GitHub in the code repository, and then we have some CI, continuous integration pipelines running, and ultimately triggering a Spinnaker, which is a deployment automation tool to deploy the configuration automatically in Kubernetes. That's the first case. The second case is almost the same, but instead of having Spinnaker, we are using some bash logic, wrapping kubectl to apply like more granularity with our manifest. And the last part is when the developer or user apply directly to the cluster using kubectl. So how do we protect that? On the first two pipelines, we have linters that are running at CI level and taking the GitHub configuration. So we can have some validation at that point. But what about the third pipeline? Like we don't have linters because it's on the workstation, on the user workstation. So he or she can do whatever they want to apply. So how do we protect that? We use admission controllers. The great thing with admission controllers is that it's a last line of in-depth defense. It will always be checked at last. So it can be used for both like CI pipelines or like standard apply by users. But when we are thinking about the user experience, we need to think about the feedback loop, which is the speed at which there is a feedback with a given change. Does it works well? Is there any error? And we want this to be as short as possible. So in the first two pipelines, we have it at linter level. So it's pretty quick. In the PR, the user gets the feedback that something is wrong, so they can just send a new commit and fix it. But when we rely on the admission controller, it's the worst case because it happens after the configuration is applied to the cluster. So if you merge the PR and the PR failed because of the admission controller, you will have to create a new PR, and it creates a really bad user experience. You don't want to wait for the admission controller to have those errors. So about the linters we are using, we use conftest, which is a kind of standard linter, and also an in-house, but also open sourced linter called Stain for some custom logic, opinionated logic. And so the great thing is that it's early feedback in the PR. And it checks the configuration with validation logic. So below is an example of what we have. We have a bot logic that generates a comment in the PR and sends the result for conftest. So you can see some examples of rules that are currently violated. So it means that the PR will not be able to be merged because those policies are violated. The second one is admission controllers. We are using Gatekeeper. So instead of linters, on the opposite on linters, it's a late feedback, as we said earlier. You need a new PR to fix it. But the great thing is that it not only validates the logic on the configuration, but it also reconciles with existing configuration. So you can compare existing configuration to make sure you protect your resources. And we can see the same thing. Earlier, it was a conftest result, and now we have a kubectl comment result. So that's what's happening. We have one decision rule that got created, but a Vato service got some issues, so the Vato service got denied. So you would have to create a new PR to fix that Vato service. A bit more about the linters and admission controllers we're using. I think a lot of people heard of Open Policy Agent. Today there are several sessions. So one of our coworker that will present about a bit more about how we use OPA in detail. The common language for OPA is Rego. It's a bit difficult to tame. It requires some time to make something working. But in the end, it's maybe worth it because it's pretty powerful since you can use those Rego policies for both linters and admission controllers. And also, the Gatekeeper can cache the Kubernetes resources, which is equivalent to creating an inventory of resources, and you can compare the input with this existing inventory. And that's a very important point for Istio policies. We will go now into several rules we are creating for our clusters to protect Istio and the users. So we have 5 rules today to show. The first one is about restricting Istio virtual services and destination rules to use the local namespace hostname. Why we do that is because we want to enforce the ownership of defined paths under one namespace and to prevent path hijacking. So each namespace, each microservice should own its own path, and we enforce it through the host name they are using for their configuration. So we have 2 examples, one working example and one non-working example. The first one is we are in the namespace A, and I want to use a service called service A, which is in namespace A. So this is the FQDN, fully qualified domain name notation for the service. And that's what we're using to enforce that. And in the second case, I'm in the namespace A, but I'm trying to use the namespace B service. And that's where we deny the creation for that. So we are forced to use the FQDN notation with a combined Rego rule to support this. So we also have we must use FQDN. You don't have to use FQDN initially in Istio, but we force it for both clarity and for this kind of rules. The second rule is about restricting the in-use destination rule subsets modification. So what it does is it prevents the traffic disruption when you modify a subset that is already used by existing virtual services. So here we have on the left one destination rule, test, and one subset called v1. And on the right side, we have a virtual service consuming that destination and consuming that subset. So what happens is someone try to change the subset at destination rule level to v2. If they do that, we saw earlier in the example that all the traffic will be dropped. So we block this modification because virtual service is using v1. So we actually protected from a misconfiguration to drop unexpectedly the traffic. The third rule is about restricting the configurable fields in virtual service and destination rule. The main reason we do that is that earlier we discussed about our Istio approach to gradually enable features, and enabling all features from the start in virtual service and destination rule is pretty difficult. We would be totally overwhelmed by the number of configuration users can do. So what we do is we have a whitelist of fields that users can change, and it checks if a destination rule or virtual service uses those whitelisted fields. This case works, everything matches the whitelist, but then our users want to create a new file or update the file with a new setting called export to. Export to is pretty powerful. There are a lot of use for that, but it's easier to misuse it than to use it properly. So this is one of the case we block this kind of fields. And in the future, when we support better and we are more mature in our usage of Istio, we will open more and more features. The fourth rule is about restricting the virtual services from using a non-existing subset. So that's basically the same case as the second rule. We don't want a virtual service to sync the traffic into something that doesn't exist. So the same case as rule 2, we have the same destination rule and virtual service with the subset v1 defined in both. But this time, we are trying to change it on the virtual service side, changing to v2, and it is blocked by Gatekeeper or by the linter because it's already it's not in use by a destination rule. So there would be no subset to handle that traffic. And the last rule is about restricting the duplicate hosts in virtual services and destination rules. The main reason we are doing that is because when you have different virtual services, for example, that have the same host, the behavior is unpredictable, and you will likely face issues with some traffic hijacking, and very hard to troubleshoot and understand by anyone. So in this case, we have two different services, test and test v2. So it causes no issue. But when someone tries to use the same host, test, in both virtual services, then it will be rejected. The latest created virtual services will be rejected. So that's it for the rules. There are a lot of other rules we are still thinking of, but it takes some time to develop them, especially because of the Rego learning curve. But it's very powerful. So the takeaways about protecting Istio is that first, make sure to have all Istio changes through versioning with a PR process, but it's not enough because human review is also error prone. So you need to enforce the use of continuous integration tools by leveraging linters to catch the issues at CI level and keeping the feedback loop short as possible. And the second is to leverage admission webhooks to protect the resources and to check what cannot be checked at the linter level with an inventory. Finally, a summary. The final takeaways is that first, guardrails are for both operators and users. We often think about the user side mostly, but we have them on operator. What are they on the operator side is what we explained earlier. The maintenance process to make sure you don't make any errors in change or like unexpected behavior. The observability to make sure you can see and observe what you're changing, and using acceptance testing to help with the observability. On the user side, it's about limiting the exposure of resources to limit the cognitive overhead for your developers and reducing the errors, about making the safe policies at both CI, linter, and cluster level with admission controllers. And finally, to keep a good user experience, to retain your users by having short feedback loops. That's very important. You don't want your users to be pissed every day because they have that much time to wait before fixing issues. That's it for today. I'm really happy to have you today, and I wish you a wonderful day. Thank you very much.
Thank you for your presentation, Raphael. There are no time now, so the session will be ended. Can you leave here already? Thank you so much for today, and I really appreciated your time.
Thank you very much. Don't hesitate on Twitter if you want to ask any questions. I will be really happy to answer everything.
Thank you.
Thank you.